Pumps. They come in all shapes and sizes, and they're essential to all industries that move liquids. Industries such as refining and chemical processing, water treatment and distribution, and utilities, to name a few. Pumps are used to move raw materials through various processing steps, and to move the liquids that control processing, such as cooling water. Without pumps, transporting liquids through pipelines would be impossible.
A pump may be defined as a mechanical device that adds energy to a liquid.
The energy to drive a pump may be provided by an electric motor, a steam turbine, or an internal combustion engine.
In any case, a pump must be viewed as being part of a complete system, consisting of the liquid supply, the suction line, the pump and driver, and the discharge line. As we'll see later, each part of the system affects the operation.
There are several types of pumps, but generally they can be placed into two classifications: positive displacement and centrifugal.
Positive displacement pumps operate by reducing the volume of space within the pump that the liquid can occupy. The piston forces the liquid from the cylinder into the discharge line. This type of positive displacement pump is called a reciprocating pump. Centrifugal pumps move liquids by increasing their speed rather than displacing or pushing them. Exactly how this is done and the variables affecting the operation are the main points of this program. Centrifugal pumps vary greatly in size and capacity, from very small pumps which pump only a few gallons a minute to very large pumps like this one, capable of pumping thousands of gallons a minute.
Most centrifugal pumps fall into the 30 to 1,000 gallon per minute range.
Operation of a centrifugal pump is not a simple matter. Improper operation may damage the pump and could bring the process to a complete halt.
In order to help you safely operate centrifugal pumps, this program will cover the basis of pump design, operation, priming, and start-up and shutdown procedures. But before we get into these, we need to cover some basics about how liquids behave. Stop the tape now and turn to Section 1 in your workbook. We've said that centrifugal pumps add energy to liquid by increasing the liquid's velocity. Let's see how that works.
Most of us are familiar with centrifugal force. This is the tendency which pulls a rotating object away from the center of its spin. If you allow liquid to drop onto the center of a rotating object, it will be hurled away from the center. The more rapid the rotation, the higher the velocity of the liquid as it spins out. The same principle applies in a centrifugal pump. As liquid enters the pump, it strikes a whirling disc called the impeller. The impeller spins the liquid outward into the casing, where it's forced through the discharge port at higher pressure.
Let's take a closer look at the parts of the pump. First, let's consider the casing.
A function of the casing is to reduce the velocity energy of the liquid and convert it into higher pressure. The casing shown here uses a volute design to make this conversion. Another way to convert velocity into pressure is to place diffuser vanes in the casing which slow down the flow, causing the pressure to rise.
Before continuing with various centrifugal pump descriptions, there's a new term to define called axis of rotation.
Simply put, a line down the center of the shaft of the pump and driver would represent the pump's axis of rotation. Pumps are often described in relation to this axis. As you probably noticed, the casing must be split in some way to allow insertion and removal of the impeller. When the split is perpendicular to the axis of rotation, we call it a radially split casing. In a radial split casing, the casing is generally solid around the impeller, but the end is removed to gain access. Sometimes this is called a vertical split. The other type of casing is split parallel to the axis of rotation. In this case, the top of the casing can be removed to gain access to the impeller. Another variation in casing design is the location of the suction and discharge nozzles. The most common is the end suction type, in which the suction nozzle is located on the end of the pump and the discharge nozzle is located on the side, pointing upwards.
However, the discharge nozzle may be positioned in any angle or direction to accommodate piping.
Just as there are variations in casing design, there are also several types of impellers.
Impellers are first classified by inlet design, either single suction or double suction.
In a single suction impeller, liquid enters the suction eye on only one side. For the double suction impeller, the liquid is allowed to enter on both sides. It's really like two single suction impellers placed back to back. A second classification is made by the shape of the vanes. While there are some variations, the most common by far is the radial type. Impellers also vary in their mechanical design. There are three basic types: open, semi-open, and closed. An open impeller basically consists of nothing but vanes. A semi-open impeller has a back wall called a shroud and is closed on one side. A closed impeller has a shroud covering both sides of the vanes. It's open only at the suction eye and closed to the tips of the vanes. The pumps you've seen so far have been horizontally mounted. The axis of rotation is parallel to the ground. Centrifugal pumps may also be mounted vertically, so their axis is perpendicular to the ground. If a pump's capacity is great enough to satisfactorily transport a specific liquid at a reasonable pressure, the pump may be operated independently. In many cases, however, multiple pumps may be required. When pumps are operated in series, the discharge of the first pump provides the suction for the second. This arrangement is used to increase the pressure over that of a single pump. They may also be set up in parallel where both pumps have a common discharge. This arrangement is used when an increase in volume is required. A multi-stage pump may be used when higher discharge pressures are required. This pump is like several single-stage pumps operated in series, but the impellers are mounted on a common shaft and enclosed in one casing.
Let's take some time to review and further explain the features of centrifugal pumps and the ways they can be operated. Stop the tape and turn to section 2 in the workbook. So far in the program, we've talked about the major components of the centrifugal pump, the casing and the impeller. Now let's take a look at some other important parts of the pump.
The casing and the impeller are the only parts of the pump which are in contact with the pump liquid. For this reason, the casing impeller assembly is called the liquid end. The part of the pump extending back from the casing toward the driver is called the frame assembly. The frame assembly provides support for the shaft, which extends through the casing wall and frame and is coupled to the driver. It includes the packing box or mechanical seal and the bearings. The packing box is a cavity which surrounds the shaft at the point where the shaft exits through the wall of the casing. In some cases, it's filled with rings of flexible material called packing, which form a seal to prevent the pump liquid from leaking around the shaft. The packing rings are compressed by an adjustable packing gland so they fit snugly around the shaft, but not so tight that they create excessive friction and wear it out. The packing may be lubricated by the pump liquid that leaks into the packing box, or an external lubrication system may be used. In this case, a Lehman ring is installed at about the center of the packing. The Lehman ring has holes in it to allow the lubricating liquid to pass through to the shaft. If external leakage of pump liquid must be prohibited, then a mechanical seal is used instead of packing. The mechanical seal has two sealing surfaces, one a very smooth, hard-faced metal, and the other a non-metallic material such as carbon. One of the sealing elements is allowed to rotate with the shaft, while the other is held stationary. The sealing surfaces are held in contact by springs. Bearings are a critical component in any centrifugal pump. The bearings support the shaft, and if lubricated properly, allow it to rotate with minimum friction. They also restrict undesired movement of the shaft. Because of the various forces acting on the shaft during operation, the shaft will tend to move back and forth along the axis of rotation. It also moves up, down, and sideways. Movement along the axis of rotation is called axial movement, and movement perpendicular to the axis is called radial movement. Pumps are provided with radial bearings to control radial movement of the shaft, and thrust bearings to control axial movement. The most commonly used bearings are the anti-friction type, such as ball and roller bearings. On larger pumps, sleeve bearings may be used. Many shafts are provided with a thrust collar, which limits the axial movement of the shaft. Others use another type of mechanical design to provide this function. The most important thing to remember about bearings is that they all need lubrication. Without lubrication, any bearing will be destroyed after just a short time of operation. These bearings are lubricated by oil, which is splashed onto the shaft by oil slinger rings as the shaft rotates. Some bearings are lubricated by a pressurized oil mist system. The oil is distributed to the bearings from a central reservoir by way of an oil mist generator. Bearings may also use a grease lubrication system. The bearing housing is provided with a grease fitting, and the bearing should be greased regularly. On some pumps, usually double suction, the shaft extends through the casing. In such cases, there are bearings on the outer end of the shaft. The bearing on the outside is called the outboard bearing, and the one between the pump and the driver is called the inboard bearing.
Now let's stop and review what we've covered so far, and then move on to some additional information about packing boxes, packing, mechanical seals, and bearings. Stop the tape and turn to section 3 in the workbook. Up to this point, we've defined a pump as a mechanical device that adds energy to a liquid in order to move it from one place to another. We've also pointed out that a pump has to be viewed as a portion of a system consisting of a supply, suction, pump and driver, and discharge. In this segment, we'll see why this approach is needed. In the pumping system, the driver is used to convert electrical or heat energy into mechanical energy. This mechanical energy is then converted by the pump into hydraulic energy to move the liquid. The liquid's hydraulic energy exists in two forms, velocity and pressure.
Velocity is a form of what we call kinetic energy. This is energy of motion and is measured in feet per second, or in the case of liquids, in gallons per minute. Pressure, on the other hand, is a form of potential energy. The potential energy of a substance is a result of its position. This 2-ton block has the potential of doing quite a bit of damage, since it is positioned above the ground. We say the block has potential energy. A column of water stored in a tank also has potential energy. We can measure this potential energy in terms of pressure, or in units of height or head. The pressure that is exerted by a column of water is determined by the height of the liquid or head. The higher this column is, the greater the amount of pressure that will be exerted at the bottom of the tank. In the case of pumps, the potential energy of a liquid is usually measured in units of head. In order to fill this tank with liquid, the pump would have to provide 30 feet of head. But suppose we're pumping liquid from one tank to another. The tank on the left is already providing 15 feet of head, so the pump only has to provide an additional 15 feet of head to fill the right tank. The pressure of the liquid entering the suction of the pump is referred to as suction head, and the pressure of the liquid leaving the pump is referred to as the discharge head. The difference between the suction head and the discharge head is the total head. So, total head is what tells you how much work a pump must actually do to move a liquid. If the pump is located above the suction, the liquid must be lifted, or more accurately pushed into the pump. We say it's pushed because atmospheric pressure exerts a force on the liquid. Atmospheric pressure is 14.7 pounds per square inch at sea level, which is sufficient to raise a column of water 34 feet into a vacuum. This same force helps to push a liquid up into a pump. An area of low pressure exists in the suction eye of the pump due to the high flow velocities that are generated here. So, liquid under atmosphere pressure tends to flow up into the lower pressure area. In a suction lift system, the total head produced by the pump is the sum of the suction lift plus the discharge head. A pump is sized to meet specific pumping conditions. Normally, it will be required to provide a certain discharge pressure and/or provide a certain flow rate, depending on the requirements of the system in which it is being operated.
But, as we've seen, the total head required is dependent on the suction head, so pump performance is variable. And there are other factors, such as flow rate, horsepower, friction loss, and pressure in the discharge system that affect pump performance. Pump manufacturers provide set performance curves which show how the pump will perform under various conditions. Let's take a closer look at some factors that affect pump operation and performance. Stop the tape and turn to section 4 in the workbook. Now that you know what centrifugal pumps do and how they operate, let's move on to pump priming and basic startup and shutdown procedures. First, a centrifugal pump will not operate unless the casing is filled with liquid. Before a centrifugal pump is started, it must be primed or filled with the liquid to be pumped.
In most systems, there are built-in mechanisms for priming the pump. For example, if the suction supply is above atmospheric pressure, the pump may be primed by opening a vent at the top of the casing. This allows the air or other trapped gas to be vented out of the pump and the liquid to fill in. If the pump takes its suction from below the pump can be filled by some sort of vacuum-producing device. As the air or gas is removed from the casing, the liquid will enter as a result of atmospheric pressure. This is similar to drinking through a straw. Many facilities have a central vacuum system, which is used for priming pumps. There is a vacuum line connected to the pump discharge line, And to prime the pump, you open the valve on the vacuum system. Some systems have a foot valve installed at the bottom of the suction line. The foot valve is basically a check valve which opens one way. When the pump is stopped, the foot valve closes to prevent the liquid from flowing back into the tank. If the valve doesn't leak, the pump will always be primed. Other systems may use a priming tank between the suction and the pump. As the liquid in the tank is sucked out by the pump, a partial vacuum is created. The liquid in the reservoir is then forced into the tank by atmospheric pressure.
In any case, no matter what type of priming is used, remember, priming the pump before starting is absolutely essential. An unprimed pump will, at best, be inefficient and most likely won't move any liquid at all. And running a pump without liquid will damage the pump. Now, let's take a look at pump operation, startup, and shutdown. Centrifugal pumps are usually selected for a given flow capacity and total head, or pressure capacity when operating at a given speed.
These conditions are called the rated conditions of service, and are the conditions under which the pump should be operated for peak efficiency. If operated under conditions other than its rated conditions for long periods, the pump will be damaged and maintenance costs will rise. In addition, pumps should always be operated in accordance with standard operating procedures for starting and stopping the pump. Failure to observe standard operating procedures will result in serious damage. Before you start the pump, you should always check to see that lubrication is available to all bearings. In oil-lubricated bearings, check the oil level in the bearing housing reservoir and add the proper type of oil if necessary. For pressure or mist systems, check the level in the reservoir and be sure the mist generator system is operating. If the pump is cooled by water, open the inlet and outlet valves to allow the cooling water to circulate. Also, open the line which circulates sealing liquid to the stuffing box. Pumps which are used for pumping hot liquids must be warmed before the pump is started. This will prevent damage to the pump by unequal expansion of parts when the hot liquid enters the pump. If the pump is used for hot liquids and is not always kept at operating temperature, open the warm-up valve. This may prime the pump as well as warming it. When the pump is warm, close the valve. Next, close all drains and open the suction valve to the pump. Then prime the pump. Be sure the priming is complete before starting the pump. Some pumps are equipped with a recirculating line that recirculates liquid from the discharge back into the suction line. The circulating line should be opened before the driver is started to prevent operating the pump against dead shutoff. Now start the motor. Or, if the pump is driven by a steam turbine, start the turbine following standard practice recommended by the manufacturer and your operating instructions and procedures. After the driver has started and is operating correctly, slowly open the discharge valve. Observe and listen to the pump and driver to be sure they're operating correctly. Check that the discharge head is normal and for excessive leakage around the packing box. Adjust the sealing liquid valve to be sure that the sealing liquid is flowing at the proper rate. After you're assured that the pump is operating correctly, close the recirculating valve.
Shutdown is basically the opposite of startup. First, you open the recirculating valve.
Next, close the discharge valve slowly until closed completely. Then, stop the motor or turbine. If the pump is to be kept at operating temperature, open the warm-up valve and shut off the cooling water supply to the bearings and packing. Finally, close the suction valve and open the drain valve if appropriate. Be sure that the liquid is drained into the proper sewer.
These startup and shutdown procedures are applicable to most situations, but may vary slightly from pump to pump depending on installation and type of service. Always check your specific procedures. One additional aspect of centrifugal pump operation to consider is called cavitation.
Simply put, Cavitation occurs when some of the liquid being pumped flashes to a vapor in the eye of the impeller. Vapor bubbles form and then quickly collapse. When cavitation occurs in the suction section or at the eye of the impeller, the vapor bubbles are carried into the impeller. As the pressure increases, the bubbles collapse in the vanes and the liquid rushes in to fill the void with such force that it knocks off small pieces of the metal vanes, which causes pitting and erosion.
Cavitation may be indicated by a crackling noise in the pump and by rapidly fluctuating suction pressure.
Cavitation can be corrected by either increasing the net positive suction head available or reducing the net positive suction head required. Net positive suction head available may be increased by increasing the liquid level or pressure on the suction side of the pump. The net positive suction head required may be decreased by throttling or closing slightly the discharge valve, thus reducing the liquid flow.
In any case, cavitation is a serious operating problem and will lead to mechanical failure if allowed to continue.
In this program, you've learned how pumps add the energy necessary to move a liquid from one location to another. You also learned how certain pumps make use of centrifugal force to add velocity to a liquid in order to move it, and how various types of impellers and casings may be used in the design of centrifugal pumps. You learned the meaning of the term head as it is used in reference to pumping liquids, and how pump performance curves may be used to help set a pump to perform at its best, given other operating variables. Finally, you learned various methods of priming a centrifugal pump and why this is important, and some typical startup and shutdown procedures.
Pumps play a vital role in any industry that requires moving a liquid from one place to another, and your role is equally important in assuring that this operation takes place safely and efficiently. This concludes the video portion of our program. Now go to your workbook and complete the final segment. Thank you for watching.